Good morning. So today we are going to going to look at in detail the airplane stability of your vehicle model. So we can call that as the airplane model for vehicle stability analysis, which is not new for you. Already we have looked at that model, which is our good old bicycle model. So where in bicycle model we have not considered the suspension system of your model vehicle, and the vehicle is considered to be one rigid body vehicle, where the distribution of the load of the vehicle is in front axle and the rear axle. And the front axle two wheels are collapsed to single wheel, and the rear axle collapsed as a single wheel. That's why we call that popular model as a bicycle model. With the help of bicycle model, we have looked at the dynamics of your vehicle under hard and mid speed cornering, and we were able to get the vehicle transfer function. We were able to get vehicle response, and the response what we have got is for a steady state condition alone, so that the problem becomes simplified. If you have to get your vehicle response, it will normally have two parts of response. One is transient response, another one is steady state response. So the transient response will not be prolonged for longer time, and it will die out. And steady state response is what is going to be there in your vehicle if you are intended to have your vehicle mode of operation under cruising speed, constant speed in a curve, right? So when you are accelerating or decelerating a vehicle in cornering, then there is a transient effect. And that transient response altogether, it is going to be more involved problem. And we are just going to restrict our study with confined to our syllabus restriction. So we have dealt with detail steady state cornering alone. But however, one can extend the understanding of what you have learned so far into finding out transient responses as well. So for example, if you are going to simulate your vehicle motion, using a multi-body dynamics software like CarSim software, you would see that these responses, what do you mean by these responses? Yaw velocity response or lateral velocity response. And these responses will be first will have a transient effect, and then you see that would go to a steady state value. So which we will witness with the output plot of that software, but in reality, you have to work out, you would essentially use an important matrix called the state matrix, right? So that application of state matrix and the representation of your governing equation of bicycle model in state space form, all we have understood in the due course of last 10 lectures also. And today I'm going to be very specific for this lecture to looking at transfer function of your vehicle model. And then again, looking at an eigenvalue analysis, where it is essentially going to be your yaw plane stability analysis. As we have learned, your governing equation for steady state condition or pure cornering, there are two equations that we have considered. You know that if you do not give any input and your vehicle is undergoing some oscillation, and that oscillation is under about an equilibrium position, then it is stable. If it is not so, that vehicle would undergo an unstable state. So we have looked at one of the important tendency of the vehicle called an oversteer tendency of the vehicle. And the vehicle by design itself can have oversteer tendency of vehicle, particularly the vehicle which is rear engine, rear drive vehicle. If you look at, they are more of oversteer tendency vehicle. And race car, if you look at, they are again designed for oversteer tendency vehicle. These all are for a specific purpose. At that time, when you have to negotiate your car, you are going to increase, instead of increasing the steering angle, you would decrease the steering angle, that we call it as counter steer and so on. Right. So if your vehicle is designed like that, is that vehicle going to be always stable when you are operating? Is that going to be experiencing some unstable situation? Of course, it will be. So what is the parameter that deciding the stability of your vehicle? So what would be the values that range of values with which you can expect the stability of your vehicle and so on, is what is something an interesting part of our study. That's where your dynamics understanding is not only alone sufficient. You also have to have an understanding of control system. So there are students from our department have also opted an elective in automotive control system. So wherein you would be studying that in more detail. But however, today's lecture I'm going to extend from where we left from the last class, and so that you will have some flavor of control system, and the state equation means what, output equation is what. So have a kind of clarity, the simple basic, which can aid you to go further. No, if you are to pursue your project or you want to work and excited to work, continue working in this area, you would be comfortably able to go through the textbooks and literature to follow. So that's what is the idea and objective of this particular lecture. I would share my slide and go ahead straight away to explain you. So this is lecture number 32, and today's date is 10/11/2021. So before getting into today's lecture, let us look at what we did in the last class quickly, and then we will continue, right? So look at in the last class, we looked at what do you mean by vehicle stability. So the vehicle stability is ensuring the vehicle would be under equilibrium always, and it would go under the expected motion. So for example, in this diagram, if you look at when the vehicle which is going in a straight path and subjected to a wind gust in side direction, and then the vehicle would respond according to the nature of the vehicle. So if it is a understeered vehicle, it would be going away from the disturbance. If it is a oversteered vehicle, because of drifting that can take place, or the yaw couple which is created clockwise would make this to get into the disturbance, and that time there is a chance that you would have your vehicle going to be unstable state, and it may not come back to the straight path. That means the driver cannot exercise his steering easily, and that is going to be dictated by a particular speed called a critical speed. So that's what you have seen. So critical speed. So that's what you have seen is given by 1 by minus K3, where K3 is what is we call it as stability factor. We have just already seen this, and today we are going to look at in generic way, how do you look at an nth order system for stability analysis, and then appreciate the application of your state equation or the state matrix application, and we will end our lecture with understanding an important stability criterion called Raoult stability criterion. So this is what is the content of today's particular lecture, and understanding what do you mean by yaw plane stability. And we had looked at in the last class, an nth order system can be represented by an ordinary differential equation. On the left hand side, you have your state variable x here, or you can call it as a q, whatever that it is there. So the left hand side equation is what is your governing equation, and right hand side differential equation is a generic input to the system. So it is nth order m order input differential equation, and these are an ordinary differential equation. Right, so a control system of your nth order system can be simply represented by this way, where you have your output is obtained by multiplying the input with the transfer function of the system. So you know what do you mean by transfer function of the system, because we have just looked at in our bicycle model, the transfer function of the system is r by delta or v by delta. So we had essentially there is a numerator polynomial and denominator polynomial, correct? So we had here a polynomial and here a polynomial, and this denominator polynomial is what was called as characteristic polynomial, right? And to get this transfer function, we have used something called Cramer rules, so that you are able to represent the individual state variable as a ratio of two polynomials. So this is what we have looked at. I just to take you there what we have seen in this lecture, particular lecture 23, we have looked at that so that it would be easy for you to follow. So we were knowing these are the important equations. So first equation is what is coming from its kinematics itself, wherein this is fundamental governing equation for steady state motion. Whereas it is pure cornering and your speed is constant, and then you have your 2 degree freedom model, bicycle model. We had these 2 and 3 two governing equation, and they are essentially obtained in a state form equation itself explicitly from these two equations. Fy is equal to mv dot plus mru, and mz is equal to iz z r dot, and your FIF and FIR, AFIF and VFIR all coming from your bicycle model free body diagram. And then we were also able to represent this equation 2 and 3 into the state space form, and we defined this as a state equation. Right. So, you know, in this, the A is what is called a state matrix, and that will be given for a given vehicle, bicycle model by the vehicle parameters. What I mean by vehicle parameters, mass is there, mass, moment of inertia, about an Z axis is there, and you have your dimension geometry, A, B is there, and you have if AB is there, you can also have no, that is essentially bringing in your axle to axle dimension. A plus B is what is L, you know, that's what is called wheelbase. And you of course have a C alpha F, C alpha R are representing your tire cornering stiffness values, and U is what is the forward speed. So this is all vehicle parameters, and this state matrix is very good matrix and to characterize our system. Right. So for a steady state cornering, this is that set of equation, and this equation essentially nothing but your equation number 6. This we have seen, and then we continued that day looking at the two equations. See, if you look at these two equations are of single order, first order equation, because the derivative is first order. But if you look at these are made into two single order system, first order system for a second order equation. Bicycle model essentially should be of second order system. As you know, this parameter here, V dot is acceleration, but we take V dot, V and R as state variable. So here we get straight away the form of state equation. But it may not be like that for every situation. When you consider especially nth order system, we have to convert that nth order ordinary differential equation into n single order equations or n single degree freedom equations. Like this second order system of your bicycle model has been represented by two single orders of these two equations, 2 and 3. We would be able to write for an nth order system, right? And we have again looked at the equation can be represented in this linear algebraic form, algebraic equation. And you see on the right hand side what we have is an input. When you make this input 0 and you look at your equation, and that's going to be your characteristic polynomial. Or if it is for differential form, it is an ordinary second order homogeneous equation. And that equation is what is to be considered for your eigenvalue analysis, that is going to give you your stability criterion or stability analysis, that will lead to a stability analysis. So we have looked at here how this transfer function lateral velocity for the given steering angle input can be represented by these two ratios of determinants by grammar rule. And similarly, we have got it. So in this, you know, denominator polynomial is this delta given by this. We have got that. So anytime for a bicycle model, you should remember this delta. So you have coefficient for s squared, coefficient for s, and you have a constant term. And there you define what is this K3 as stability factor, right? So stability factor. There is a relationship between stability factor and your understeer gradient. No, that also we have seen in one of the lecture. So what does that, why do I, just to show you this once again, is because you need to understand the transfer function of the system is very vital. Whenever you have to represent your dynamic system as a control system model. So that's what we have seen in the last class. We require to represent into this form. So if you have to represent governing equation of your dynamic system into a block diagram of a controlled design, and that would aid you to go further to have a required controlled motion of your vehicle or required controlled parameters, operating power plant system and so on. So generic. So control system is everywhere in today's scenario of mechanical system. So we were able to get the transfer function here, what is required, called a closed loop transfer function, if it is of simple bicycle model by Cramer rule. If it is really of an nth order system, here what we represented, and the nth order system closed loop transfer function can be of ratio of two polynomials, and there we defined the denominator polynomial is what is characteristic polynomial. Right. So how do I get the transfer function for this? So one is taking substituting trial solution here or taking Laplace transform on both sides, you would be able to get, and that's what we will see. How do you have parameters that parameters of the vehicle or input matrix or an output matrix, whatever that I get for the system, all can be nicely organized, put together, so that they are all relating to your transfer function and so on. So that is what is the objective of today's particular lecture that we are going to do. Right. So let me take